Okay, so welcome back, everyone. This is the final session of today. We're going to be looking at the statistics part of the applied course. Just a quick reminder, as I just said, tomorrow's session will start at 9 a.m. So anyone who's joining that as well, just be aware it's a slightly earlier time. We're going to go through the statistics now. And then at the end, I'm going to put the link back up for the survey. And if we could get your feedback, that would be brilliant. And then after the feedback comes through, we'll send out the solutions to the mini mocks. So hopefully you've been able to use those as good consolidation questions as well. Right, so let's look at the statistics, data presentation and sampling. As I'm sure you're aware, being very sort of fluent and competent using your calculator is important for the stats part of the applied course. Now, I know this has been quite a full-on day, quite a full-on afternoon of applied, and a lot of people do find the applied course quite challenging now because we have the mechanics and the stats in there, and they're very different elements of mathematics. They're two very different skills. What we're going to be focusing on is we're going to look at statistical sampling, ways of analyzing data, and also representing data with cumulative frequencies and histograms. This does come up in the exams. These are kind of key topics to look at. And we're going to go through in a very kind of exam focused way again. Okay, so let's make a start. So again, all the exam boards require these keywords. And this is something that I would say is a real focus for stats. Understanding the definitions, putting things in a context. They are quite picky with marks. So we need to be bang on with this. In the same way that mechanics, modeling assumptions and force diagrams and notation is really important, statistics can be very picky on these very precise points as well. So just looking in general, population and sampling, some of you will have seen this stuff in other A levels as well, but these are kind of key terms that we need to know. So the population is kind of everyone or everything. It doesn't have to be people that we're dealing with. So sometimes it could be, if it was in marketing, it might be to do with the products, but population is all of them. A sample is a sort of subset of that group. So we might have a sample here. And then what we have is a census is collecting the data for the whole population. So the population is the whole set of items that we're concerned with. The sample is a selection of observations from a subset of the population, and we use that to deduce things about the whole group. And then a census is taken an observation for every single member of the population. And what we're always looking to avoid and we're trying to look for is not having bias. So bias is a cause of results of a sample not properly, truly representing the whole population. So if I wanted to understand how different age groups engaged with technology, I wouldn't just ask all the people of the same age. That would be biased and it wouldn't be representative of what I was looking for. So that's hopefully nice and clear to start with. The other thing that can come up in stats, and these are normally sort of maybe 2-3 marks, potentially 4 marks, are advantages and disadvantages of sampling techniques, but also samples and censuses. So hopefully these are quite quick to go through, quite clear. So a sample is quick and easy to carry out, and it's less data to process than a whole census. The disadvantages, as we've already said, is it could be that it's susceptible to bias, or it could be inaccurate. It might not truly reflect the big picture, especially if you take a really small sample or you don't do it in a random fashion. It might end up being a biased little quick survey. So a census should be a perfectly accurate result with no bias. But in order to achieve that, it's very time consuming and potentially expensive. And there's lots of different costs. And this is an important point. This is something a lot of people forget. Because when I've mentioned this before, people have gone, "What? How can it be destructive? The census isn't destructive." It can be. If we're thinking about a census that you answer in your house on a bit of paper, that's not what we're talking about. If the census was actually to trial food, for example, or test out items you're going to sell, you have to do a sample. because if you tried all the food, you've eaten it all, you've got nothing left to sell. So sometimes the process of doing a survey or a census can be destructive. So that's like you can't then sell that item. So that's why it's sometimes a disadvantage. And that's the one people do forget about. Now, here's a good question. And I think I've given the game away a little bit here. But a biscuit factory produces 1 million biscuits a day. And the factory employs quality assurance testers who test the biscuits by eating them to ensure that they are good enough to sell. So for a single day in the factory, state the population for the quality assurance test, state how many biscuits would have to be tasted if we're doing a census, and suggest with reasons why we wouldn't use a census. So this is actually very quick. I've kind of given it away already a little bit, but a couple of marks, very precise, and we've just got to make sure we're clear with this. So the population is the 1 million biscuits. They're the items in our population. That's what we're dealing with. A census would be each of the 1 million biscuits being sampled, so tasting them all. So why would you not do that? Because it requires the biscuit to be tasted and eaten. They then can't sell any biscuits. So that's just putting it into a context. And that's that. I've seen questions like that come up before. It almost feels a little bit silly, but we do need to be aware. So a sample is better, especially for things like food or products you're going to sell. But even if you were dealing with finding out information about humans, it's just more sensible a lot of the time to do a sample than try to do a whole census. So that would be your answer for the final part there. Okay, so random sampling techniques. We're going to go through the different sampling techniques. And some of you, these might be things you've seen at GCSE or in statistics before, but you do need to know these different types of sampling. After this, we'll be looking at data analysis and how we represent data. But the way we sample is really important. And just beyond the scope of this exam as well, this is probably the bit of statistics that you will use if you're doing any sort of further study in science, in maths, in engineering, in medicine. If you're looking to use maths to actually test things at university and beyond, the way you sample is really, really important. So, and it can be criticized as well. So what we'll look at is a simple random sampling. This is a sample where every item has an equal chance of being selected. That's what random sampling is. So it's easy and cheap to carry out. It's free from bias. That's why we like it. But it can be time consuming from large populations. The reason it can be time consuming is if we want to ensure that it's random, we have to be very organized. So another type of sampling is stratified sampling. And what this is taking the population and splitting it into strata, which are like exclusive groups where everything's sort of categorized. So it might be by race, it might be where you're from, it might be religion, it might be anything we can kind of categorize like that, could be used for random sampling. And what the aim of this is that it actually represents the population structure. So you might stratify by age, but it should be in proportion to the real population. So if I sample 100 people instead of a population of 1 million, I should have the right quantities of the people that represent different groups. And so the aim is that it gives proportional representation of different groups. So that can be quite challenging as well. And it's sometimes not always even possible to clearly classify into distinct groups. So that becomes really hard to sample in a fair way. But the way to do this in general, depending on how we've stratified it, is the number in the stratum over the top number in the total population times by the sample size. So effectively, the proportion times the sample size will tell you how many people to pick. Okay, so we'll see this again. We'll see this idea going forward. And then we'll look at some non-random sampling techniques. So what we've got is one example is we use a researcher or an expert and they choose people in the population So that can often be cheaper and quicker and simpler than the random sampling, where we have to have all the information and do it really fairly. Quota sampling, we use a researcher, but there's a few advantages and disadvantages to this. So no sampling frame required means we don't need that whole massive register of everyone and then do it all fairly and then, be really organized. We can just let the expert choose the people. And the expert can select people based on their understanding and knowledge in the correct different groups, but it could still introduce bias. As soon as you've got someone choosing who they ask the questions to, there will be some sort of subconscious bias. Probably they might ask people that they think will respond better or will respond in a more easy to understand and easy to represent way. So that could introduce bias. That's the one disadvantage, is because someone's picking it, that could just naturally introduce bias. Also, the sample must be selected, so it could be costly and it could be inaccurate. Okay. And sometimes there could be non-responses and they're not recorded. And that might have been important that someone chose not to respond, and the researcher might just pick someone else. So it looks like everyone responded. Okay. And then there's this other type. I like this one. So opportunity sampling. So sampling where a sample is taken from people who are available at the time. So this is a little bit of a lazy one. But there are actually obvious disadvantages to this. So if you just ask the first 5 people you see, that would be like opportunity sampling, or sometimes called convenience sampling. It's unlikely to be representative, and it really depends where you are at the time and what you're doing. So if you wanted to know how many people like going to the park in the week and you ask someone on the weekend, it might not be the best kind of sample to choose. So let's have a little look at this example here. We'll talk this through together, and I'll give you a minute to have a little think. So the UK manufacturer, Broom to Breathe, are looking to get opinions from a potential customers of a new product range. So they're considering multiple ways of finding the information. For each of the following methods, determine what kind of sample is being taken and suggest a reason for or against the method. What I would say with these advantages, disadvantage questions, try not to use like a disadvantage for one as an advantage for the other and repeat yourself, because you might risk not getting all the marks. So the first one, asking attendance or attendees at a housekeeping convention, randomly selecting 100 people with interest in brooms, breaking down their customer base by age range and choosing sample groups from each. So think about what you think each of these are, and then we'll just check it. So they're basically definition heavy questions. What is a population? What is a sample? It's knowing those key definitions. So many potential customers would be at a convention. I would say this is an opportunity sample though, because you've gone to that location and just said, I'm going to ask whoever's there. So the positives and negatives of this method: quick and cheap to do. That's one of the main things for opportunity sample. It's easy to carry out. But the problem is housekeeping enthusiasts aren't going to reflect everyone. If you go and try and find out what people think of a product at a convention where people are buying that product, you're going to get a biased view. So that's really important. If they're trying to sell brooms to people that are at a housekeeping event, that's probably going to go down better than if you just did it anywhere. So that is an obvious negative. That might be so obvious we forget that that's a point to make. So 100 random people chose from the population. This is simple random sampling. Positives, easy to do without bias, might not fully represent, because again, small amount of people and so on. It's hard to represent everyone with a small sample. And then this one here, groups being broken down by age. This is a stratified sample. Population will be broken down proportionally represented. But it's maybe not the best way of breaking down it for this particular thing. So there might be age categories that literally are just zero, not interested at all. So there might be better ways of categorizing this as well. Maybe occupation, or there might have been clearer ways they could have broken it. Right, we're going to move on to the next topic, so the data analysis stuff. Whoops. So what we'll do is we're going to look at, this is normally the bit that people struggle with when they're learning the content, but actually is absolutely fine if we're confident with our calculators and the notation as well. So we're going to look at things like central tendency, sigma, kind of all the standard deviation stuff, and how the questions will use this as well. So this is really, really crucial for the course now. It always has been actually a part of the statistics, but let's have a little look. So a measure of central tendency is basically like an average. So how close to the middle are we? So effectively, the ones that we should recognize, the mode, the most common, the most popular, the median as the middle value. And this is the bit people get very caught up on, the median. There's always a lot of confusion at A level with this. So I want to just really clarify this here. So n+1 over 2 if n is odd. So there's a couple of ways of doing this. You can think of it and kind of effectively the same. If you add 1 and divide by 2, you'll find the middle. And so you can think of it as the average of if n is even. Now, the other way, like a lot of people do this at GCSE and they're absolutely fine. When it's a discrete list and you have an odd number, the middle falls very clearly on one value. When you have an even amount, it's in between the two middle values. Okay, that's fine. And that's what we've always done. And that's what we know. The thing that gets confusing at A level is actually when you have continuous data, like in a histogram, you don't do this n+1 thing because you're cutting the data almost like a cake. It's continuous. You're just chopping the area in half. So for continuous data, it's just n over 2. But what we're talking about here is when this is a discrete list of 11 items or whatever, and you have the raw data. And this is where people tend to get confused. Now, the mode and the median are two of the measures of central tendency. Another measure is, of course, the mean, which is the average. So you add them all up and divide by how many there are. We've seen that a lot in the past. Notice that there's also this notation we have to be careful of. So sigma x, x with a bar above it is known as the sample mean. And I do just want to point out while we're here, this is the notation for sample mean. If you ever see this, mu, this is talking about the population mean. So there is a difference in notation. This is the sample mean, which is the sum of all the values divided by how many you have. And this is for ungrouped raw data. And then this is for grouped data. Okay, and x being the value of the class or the item. And n is the number in the class. Okay, so if x is sorted into classes of continuous data, you choose the midpoint. So we should be fairly familiar with grouped continuous data, but we're going to see this now for finding measures of central tendency. So here we go. Here's a quick question for you guys to try. It's a good problem solving one. I'm going to give you a minute to think about it and get us into that statsy kind of way of thinking. So here's a set of data, ordered data, that's important. X, Y, and Z are distinct integers such that the data set has a mode of 6, a median of 5, and a mean of 13/3. Find X, Y, and Z. So ungrouped data, so it's just a list of different integers. We need to know definitions like the word integer, like what mode is, like what mean and median are. And no decimals, 3 different values already in order. So I'm going to give you a minute, just over a minute to think about it, and then we'll check through, see how you go, and we'll check it. Well done. Let's give it a try. Okay, so let's have a look. So it's ordered, so that was helpful. And what we can do is we can use information about the median to work out y, because y will be the median. So there are 9 data values in total. So y is the median. So straight away we can fill that in as 5. It was important that the data was ordered though. Now the next thing is we can look at the mode to deduce if there's another value to be the mode. Now we've already got 2 6s, and Z will have to be 5 or 6 because it has to be an integer. Now the problem if it's 5 is that it would then be bimodal. There would be 5 and 6 would both be the mode. So the way to ensure 6 is definitely the mode is if Z is 6. So now we've only got one value missing. So if we now know that Z is 6, we've got to use the mean, and we've got to kind of do the reverse mean, which we know is the sum of all the values divided by the 9 values must equal 13/3. So this is hopefully a relatively simple one to solve. We can cross multiply or look at equivalent fractions. But basically, times it up by 3 or times up by 9 on both sides and cancelling down, you're going to get 39 is equal to 36 plus x. X must be 3, which totally would fit in there. So that looks good. Okay, so hopefully quite a nice one. Now, what we're going to look at is measures of spread or measures of variation. So this also comes back to when you're asked to compare data. There will be 2 mark questions for this, and you have to use a measure of location or central tendency and a measure of spread. So where's the middle? So we can't just say this class are better because their class average is higher. You'd also have to say this class is more spread out. These results are closer together. So different measures of variation. One type is the interquartile range, which is the difference between the upper quartile and the lower quartile. And what this does is this actually gives the range of like the middle 50% of the data, which hopefully we've seen, of the central 50%. And then if we list all n values from lowest to highest, the way we'd do that is we look at where the middle would lie. So it'd be the middle of these two for the quartiles, the middle of these two. That's brilliant. And then that would allow us to find, just in the same way as the median, where the quartile 1 and quartile 3 lie. Now, the other measure of variation, which for a lot of people is new at A level, is variance and standard deviation. Now, these also measure spread in the data. There is a formula for them, but you're also able to do this on your calculator. So sigma squared is the variance and sigma is the standard deviation. Now, loosely speaking, the way I would understand standard deviation is like the average distance of all the data from the mean. But the reason variance is important as well is squaring allows the negative ones and the positive distances away to be turned positive. So that's sort of how we get to the standard deviation, is using the variance, but they're both measures of variation and spread. So here's the formula for the variance. And of course, the standard deviation is just the square root of that. So the standard deviation off the back of that is just putting a square root sign around all of it. So what we can think of it, this is the one for ungrouped again. And this is the one for grouped data. And then basically what we're saying is it's like the average distance, average square distance from the mean. So if you take the mean value and you take every data point and subtract the mean and square it, then add all of those up, divided by how many you have, it's like the average square distance from the mean. So this X represents all the individual values, taking the mean away to look at the distance from the mean, and then squaring it kind of turns them all positive and makes them bigger. Divided by n averages it, and then if you want the standard deviation, you square root that answer. Okay, so it's kind of like, now for this grouped one, this is basically, remember the mean itself is this. But basically what we're working out is the number in the group times number in the second group, and so on, all over, and so on. Okay, and again, we'll look at how these sort of things come up in questions. Now, more on measures of variance. If sigma is low, if the standard deviation is a low value, that actually means the spread isn't very big. So all the values are close to the mean. It's probably really important that we know how to interpret this. So basically, this is telling us that it's quite tightly clustered. And again, those of you that have done year 13 stats, you might have seen this idea a little bit when you do normal distribution. Now, if the sigma value, the standard deviation, and of course the variance is big, it means there's quite a big spread away from the mean. So the values are more spread out. So there's like a larger range. Sort of ties in. So there's more spread. If sigma, lowercase sigma, standard deviation is a big number, that means it's more spread out. Okay, so let's have a little look at the following question. Right, Arnold has recently lost his 12-sided die and plans to just use two 6-sided dice instead. So his friend Beth thinks that this is a bad idea and tries to show by rolling two 6-sided dice 100 times. She records the number of times n that the total value of her throw X in a certain range and displays it in the table, which we'll see. Calculate the variance of scores from her dice throws to 3 significant figures and use your result to comment on why the 12-sided die cannot be substituted with two six-sided dice. You may use the fact that the variance of 100 throws from a 12-sided dice is approximately 10. So they've given you that. So let's look at what we've been given. 4 marks, group data. We've got some stuff being given to us. We've also been told this. Okay, so we've got 12-sided die, two six-sided die. Okay, 100 times. Okay, so let's have a little look. Another really good, tricky question for us to look at. And I'd say the bit that's important they've given us, that of course we wouldn't have just known, is this. Okay, so we're going to use that for comparison. The variance of 100 throws from a 12-sided die is approximately 10. Right, this is what we have. So this is her results with the two six-sided die. And let's give it a go. So I'll give you a minute to have a little think, but I am keen to just walk this one through with you. So we'll start looking this through together shortly. Right, here we go. So first thing we're going to do is if we calculate the midpoints of the ranges, because this is like grouped data, and then we'll do that for each one. So add the two bounds up and half it, find the middle. So if we do that for each, we can kind of add that on for each of the grouped ones. So the 7 is obviously just 7, but obviously it's a bit of a weird setup. So we're going to use the midpoints instead. And we'll reformulate this table because this is now something you could actually even punch into your calculator if you know how to do the summary statistics on there on the one variable calculation mode. And then we're going to look at calculating the variance. So in order to do this, if you know how to do that on your calculator, you can put that table in the calculator, have the frequency column turned on, and it will tell you sigma squared is 7.095, blah, blah, blah. So obviously the calculators vary depending on what calculator you have. I think in the class whiz, it's on the stats mode. You need to turn the frequency column on, and then you fill in the table, and then you press the OPTN button and you get the summary statistics. For the class, for the CG50, it's slightly different, but there is the stats mode as well, and you fill the table in. And then the options are all sort of along the bottom. But this will just do it all for you. So this is one of those other places where your calculator is so useful for statistics. So 7.1 is sigma squared. Now we were told for a 12-sided die, the sigma squared is 10. And for two six-sided die, sigma squared is 7.1. So how do we interpret this measure of spread? Well, the variance for two six-sided dice is much lower. So this means that the values from throwing a 12-sided dice are fairly evenly spread, where the six-sided dice are much more grouped closer to the mean. So that's an important consideration. So it would not make a good substitute because it's actually a totally different way of the results are spread out. So good question to look at because it was a bit of a strange context. What we're going to do now, we'll do a little bit more on data presentation and sampling, and then we're going to get on to histograms. So we're going to look now at correlation, really easy idea that you've seen all the way through school. And it actually doesn't get much harder for this topic. Basically understanding if the gradient of the line of best fit is positive, then it's positive correlation. And if it's negative correlation. How you answer this in an exam is crucial though, because they will be picky with the marks here. You would always be needing to contextualize this. So also if they explain the relationship, you would say, e.g., for this, if it was height and weight, the greater the height, and obviously use proper words, the greater the weight, or as height increases, weight increases also in general. So this one here, this might be, e.g., as you increase your spending, the amount you have for saving decreases. That might be what that shows. And no correlation is if the scatter diagram's all spread out, there's no clear relationship between X and Y. Okay, so for outliers, this is important as well, a really clear definition here. An outlier is an extreme value that does not fit the rest of the data. So we can see one on here, but the thing that people do wrong, and I really want to stress this, is an outlier and an anomaly are different things. So an anomalous result, I'm not sure if we know the difference, and it might be that you've defined it in other subjects. An anomalous result is an error. So for example, it's like a typo or a wrong value. It can't physically be it. Whereas an outlier is just an extreme value, but it has happened. So it doesn't fit the trend, but it is actually a data point. And that's a really important distinction to make. So anomalies are actually errors and you would remove them. So removing the anomalies is called cleaning the data. But we might want to remove an outlier if it would lead to inaccurate conclusions. But we need to set a boundary of when we consider it an outlier. And there's actually no set way of doing this. So there's no single method to calculate where an outlier is. We have to sort of put parameters on this. And the way you do this will be told to you in the question. So sometimes people get a little bit flustered and they think, oh, I can't remember the definition of how you work out an outlier. The question will give that to you. So there's a couple of ways of doing it. One way is that it might be a very common way that they often use is 1.5 times the interquartile range above the upper quartile and 1.5 times the interquartile range below the lower quartile. Anything beyond that is considered like extreme. It's considered an outlier. Okay. Another way they sometimes define outliers is like the mean plus or minus 2 standard deviations or 3 standard deviations for some boards. But this varies. They'll give it to you in the question. So let's actually look at this, and they've actually prescriptively described how you're going to work out if it's an outlier. Okay, so let's look at this one. So a group of students were given a set of unknown alloys, A to I, of a metal, and were asked to basically measure the melting points. The results are recorded on the table we'll see, and the temperatures are given in degrees Celsius. And the students had difficulty working with alloy I and measured a much lower melting point. So test if the melting point is an outlier and use the standard deviation test if it's less than 2 standard deviations below the mean. Right, so I'm going to give you the data now, but we're going to use the calculator. We're going to look at finding the mean, obviously, and also sigma, the standard deviation. It's only worth a couple of marks, but we have to get this kind of bang on. So here are the values. Okay, it does look quite extreme already. It looks very different, but we don't want to jump and conclude and just guess. So I'm going to give you, again, a minute and a half. Give this a try. Try and use your calculator and get that mode sorted. And then we'll look at how we would conclude this. After this, we'll be moving on to histograms, and there might be a little bit of interpolation in there, but we'll see how we go. Let's give this a go. I'll give you a minute or so to try this out. Okay, so here we go. So if we were to input this data, they're the values of the melting points, and there's obviously just one of each. So you could find the mean, add it all up, divide by how many you have, and then find the standard deviation, hopefully using the summary statistics on your calculator, not having to do it the long old-fashioned way, just by filling in the table and getting your summary statistics from the option. And then we get sigma as 575. That's the average distance, loosely speaking, of every point from the mean. Okay, so the mean is around just under 1,000 degrees, and everything on average is like almost 600 away, taking everything into account. So a potential outlier they've defined as take the lower quartile. Sorry, they didn't define as that. And said take the mean and minus 2 standard deviations from it. So if we take 954 and we minus 2 lots of 575 away, we get minus 196. Now, minus 38.86 is not 2 standard deviations below. It is in the negatives, which looks a bit weird, but it's not as extreme as we would consider an outlier. So that was a really good one. Well done if you got that, because I think that can be kind of quite a tricky style of question. But hopefully we can see we've used that criteria there to test whether it's actually an outlier. Okay, so we used the standard deviation because that's how they've defined outliers for this question. Right, let's look at representing data. And again, a big important topic that they've put in the course is things like cumulative frequency graphs and histograms. So cumulative, remember, like accumulation, means the running total, building up the totals as we go. So for example, and hopefully we've seen this at GCSE, but for the first one, that will just be the frequency it is. For the second one, it will be the 2 frequencies as it added up. So basically a running total of the frequencies. And then, oh, messed that up. Hang on. And then what we do is it's really important we remember this. We plot it the end point of each group. So at these values, we plot the sort of height as the running total frequency. Okay, so if we plot that, what we actually end up with is normally sort of an S-shaped curve that looks like that. And for this one, it will start at the origin. These values like F1, and then this would be like F1 plus F2. This would be all of them added as they go. Okay, and so by the end, we reach the total frequency. Well, what this allows us to do, so basically the gaps between each jump, like that is F3, that is F2, that's what it rises by. Okay, but this allows us to chop this continuous data up almost like a cake, because if I want to use it to find the estimate of the interquartile range, I can sort of see how the data is behaving, the shape of the data as a curve. And the actual process is called interpolating, because what I'm going to do is I am actually going to basically go through the shape and chop it up. So if I wanted the interquartile range, it's out of 40 pieces of data, even though I don't know the raw data. I know there's 40 bits. It's behaving in this cumulative amalgamation of stuff. So what I can do is I can chop that into quartiles. Like I could even find the median if I wanted. But this lower quartile would be at 10, upper quartile would be at 30. So a quarter of the way through and 3/4 of the way through. Notice that this is the thing I mentioned earlier. You don't add the 1 or anything because it's grouped continuous data. You literally cut it like a cake. 40 bits of data all mushed together. The median's at 20, quartiles at 10, the upper quartiles at 30. Okay. So N is 40. And then we're going to plot horizontal lines and read them off. So what we've got is if I want the IQR, that would be Q3 minus Q1, which would be 15 minus 7.5, which would be 7.5. Okay, so let's have a little look. Now, hopefully that's clear and we've sort of seen that before. Let's do this question together then. So a group of 37 office workers take part in a charity marathon. After certain periods of time, the number of workers who have finished the race is recorded. The data of N against T is shown in the following graph. From the graph, calculate the interquartile range of the times it took the workers to finish the marathon. Give your answers to 1 DP. So 2 marks should be a fairly simple calculation. We're going to look at recording the results in a cumulative frequency way, which it would be if it's the times at which people have finished. The ones that finished earlier have still finished. So there's sort of a collection of people at the finish line. That's it. So we're going to use the graph to do this and check units and rounding. Really important. You don't want to do this and then lose half the marks because you didn't write the answer properly. So here's the graph. Give that a try on your copy. We'll check it in about 30 seconds. I'll start doing it. And remember, we chop it just exactly from the total amount. And there were 37 bits of data in total. So a little bit annoying, this value. But let's see how we go. Use your calculator. Do it as accurately as possible. Should be doable. Do it as best we can. So the quartiles of N, if there's 37 things, 37 over 4, so the 9.25th position, and 3/4 of 37, 27.75th position. That's how we're chopping it. So if we draw those lines on, read them down, 4.2 and about 5.9 if we're going to 1 DP. So feel free to fill that in as well. And then always try and do this as accurately as possible. But obviously we are limited by how good the graph and the graph paper they give us is. But there will be some tolerance. Normally just aim to be as exact as you can because it's a bit of a skill of precision as well. Right, so finally answering the question, sometimes people get in a bit of a, they do the right thing and they do the wrong thing. It's not the range of this. We know that this is the boundaries of where the quartiles are. It's always the interquartile range is actually the range of the values you've discovered, obviously. So do double check you don't mistakenly take the wrong bits away. Okay, so here we go. So you take those values away and use the correct units and round it accordingly to 1 DP. Okay, so very well done if you got that. And actually what the answer would accept is it would accept anything between, based on the fact you've had to read that off that graph, and you might have not got 5.9, it might have been a bit off. So they'll accept anything in that interval, actually, for this particular question. Right, histograms. So again, it's something we've seen at GCSE, but they tend to be harder questions at A level. Frequency density, do just remember, again, this is grouped continuous data. This is frequency over class width. So it's basically a bar chart, but it's not the heights of the bar that represents the frequency, it's their area. So the class width is, of course, this, the X width. And it's the area that represents the frequency. Okay, so in a histogram, the area of each bar is proportional to the frequency. And so I won't say equals at A level, I'll say is proportional to. But at GCSE, it was just bang on equal. But we can adjust the scale accordingly. So there should also be no gaps. It's not a bar chart, it's a histogram. The same thing as like cutting the cake. It's a seamless link of data because it's continuous group data. So what we've got is that this could be tied in with probability, but data can be used to predict the outcome of a random selection of a group. So if we look at, for example, this here, the ratios of the areas could be used to calculate the probability of a particular result. If you were to use the whole area as equal to 1, and we assume it's distributed evenly within the groups. So if I start filling in some values here, so say we say that would have an area of 100. This would have an area of 75. This would have an area of 100. Now, for example, this would have an area of 100. Now, if I wanted to know the probability that X is greater than or equal to 35, then basically I'm chopping it here and I'm looking at this amount, which is 50 out of the total. And I'm hoping that's kind of clear what I did. But the total frequency is the total area, and that's 50 out of that, which I believe ends up as 2/15. And then you can use a probability that you'd fall in that section. Okay, so we're going to do this with an example, another exam question now. And we'll work this last one through nice and clearly. And then, as I said, I'll talk about a little bit of a recap and then basically explain about the exam papers, the mini mocks, and also some of the stuff from tomorrow. But let's look at this question first. So a school records the grades achieved by students in a recent exam. The maximum mark is 75. To produce the following histogram, we'll see in a minute. The table shows the grade boundaries for the paper, right? There's a few things going on here. A student's paper is selected at random to evaluate the difficulty of the paper. Calculate the probability that the selected student got a B or higher in the exam. Right, I think this is great. Really good question. So let's have a little look. 2 marks, 2 steps. Probabilities from histograms like we've just been doing. And we're referring to different sort of bits of information. And we may need to look at the area of different sections. So probability, because it's greater than or equal to, we've got to look out for that. We're given a table. That's important. B or higher, got to refer to that. Let's have a look. Okay, so I think, here we go. I'll give you 2 minutes. I've maybe been rushing you today. 2 minutes to fully try and complete this question. Give it a go. I'll whiz through it nice and meticulously, and then we'll sort of look to wrap up. So give this a try, guys. Really well done. I appreciate it's been very full on today. Here's your last one, a bit of histograms and statistics. Really well done. I'll be quiet so you can focus. Let's give it a go. Right, hopefully we're getting on okay. We'll check this together now. So let's see how we're doing. So it's a bit of an interesting one because there was obviously different information. You had the histogram, you've got areas to look at. You've also got this situation of grade boundaries and stuff. So I know it's an example that actually might be a little bit close to home for a lot of students at the moment, looking at worrying about test papers and exams. But it's a good context to look at because you've got to refer to different things and also put it into a probability context. So let's have a go. Right, so let's have a little look. So the first thing, let's work out the total area of the histogram. So if we do that for each of the different classes, each of the different intervals, the width is 30 and it's got a height of 3. So it's got an area of 90. Next one, 7 wide and it's 15 high. So it's 105. Next one was we'll work out is 20 high and we'll work out the width. So it's 8 wide and it's got an area of 160 and so on. We'll work out the next one, 168 and then 242. So we need to add all of that up, find the total kind of summation of all the areas. And then we kind of know what it's out of. What is the area out of? What's the total? So the total area is 765. And the boundaries here for probability of a B or higher, well, we need to look at the different areas for those particular regions. So it's inclusive of this group. So it's inclusive of the last two values, isn't it? Now, do be really careful with this, that the boundaries are the grade boundaries. So we need to look at the areas of those two segments out of the total area of the whole graph. So from reference to the table, a B or higher is given from 45 marks. So the values included would be 168 plus 242 out of the total 765. And we should give that as a decimal. Another point on statistics, another exam point, and I've done these a lot today, I would conventionally say with probabilities, it's very normal to use like 4 decimal places because a lot of the tables at the back are, if you look at the binomial tables and the normal distribution, they're often done to 4dp. So that's just a very standard way of rounding the probability answers. Obviously, leaving an exact fraction is fine as well. Okay,